Okay, welcome back. Can everybody hear me fine?
Yeah.
Okay, so let's continue. So, hey Jacob, you there this morning?
Yeah.
I'm gonna put you in charge of monitoring the chat for me, okay? Just in case, because I can't keep all of these windows open. So if something comes up in chat that I should know about, somebody asks a question or whatever, get on your mic and just let me know, okay?
Okay.
Thanks. And okay, so um, we're talking about the consumer's utility maximization problem, and so just remember, um, and we call it the consumer choice problem. And are you with me, Emily? Are you here, Emily Cobian? Okay, maybe not. Okay. Um, let's see. Hmm. Okay, what about you, Miriam? Are you here?
Yes.
Okay, good. I have to have somebody to talk to. So, so just make sure you're following along with me, all right? So the consumer's trying to maximize their utility subject to some budget constraint, right? This is what they can afford. Is this making sense?
Yeah.
Okay. Um, and then we said that the solution to this problem is going to look like this. So we're going to have these two conditions, the tangency condition, which we already mentioned, and I don't want to write it down again, um, and the budget. And so let's see if I can go back here and copy some of the stuff that I had before. Mm. Let me select it. Uh, okay. 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 So we have to satisfy both of these equations simultaneously. So the one that I want to talk about um, is this one, the tangency condition. And so this may be a little bit counterintuitive, or maybe not. I don't know. You can tell me, Miriam, what you think. So this is the slope of one indifference curve. Okay. You see how I'm pointing to the indifference curve as the slope changes, Miriam? Yeah. Okay. But remember, I guess the real issue is like, how do we properly describe the slope of the indifference curve? Notice that along an indifference curve, what we know is true is that the utility is constant. It's some particular number, but we don't necessarily know what the number is until we are able to actually calculate how much utility is associated with any particular consumption bundle. So remember, there are a whole bunch of indifference curves here, each representing a different level of utility. So I'm going to draw two more. Does that make sense, Miriam?
Yeah.
And so what we're saying is that that the one that the consumer actually ends up consuming is going to be the one where there's a tangency here between the budget line and the indifference curve. But all of these indifference curves, remember, they have a bunch of different consumption bundles. But if we were to calculate utility at any of those consumption bundles, we'd get some constant level of utility. Like, let's say U is equal to 10.25, kind of like we did in our example earlier, where we found out that here in this first problem that utility was equal to 11.81. So I don't know if you remember that or
Yeah.
not.
Yeah.
But in general, we just don't, we know utility is going to be constant, but we don't know what it's going to be, right? So let's take a look at utility in a little bit more detail. So this is about developing the tangency condition. And specifically, what we want to know is, how do we mathematically describe the slope of an indifference curve? So that's our question. How do we do this? And do you kind of get why it's a little bit of a mystery, Miriam? Because in a linear equation case, right? So with the budget, because this is a linear equation, remember, we can solve for y and we can graph it and it'll be in slope intercept form. Do you know what I'm talking about?
Yeah.
So like for this one, right, I can just put it in slope intercept form because it's in general form. So I solve for y, and then I'll say y is equal to I divided by py minus px over py times x. And let me go ahead and reposition this a little bit. And I'll throw in some parentheses just to make sure it's clear. But this is the general form of a linear equation, which once we put it in slope intercept form, I can identify this first part as being the vertical intercept and this second part as being the slope, right? Do you follow me, Miriam?
Yeah.
But here, right, with the utility function, you know, there's no way to put this in slope intercept form. It's nonlinear. So like we're stuck, right?
Mm-hmm.
But what we can do is we can use one of our observations, and in particular, that U is going to be constant. Okay. So let's go ahead and do that. And we'll say, okay, so now we're going to say, okay, we know U is some constant. And, normally what I would do in class is I'd put a little bar over U, so you just knew it was some constant number, right? But here it's a little bit difficult because I don't have special characters. So I'm going to say it's U star. Normally I save star for the optimal consumption bundles level of utility, but I'll just say U is a constant, and let's call it U star. Okay. That makes sense? Okay. Are you following me, Miriam?
Yes.
So now I'm going to say, okay, this is U star, and it's still going to be equal to what we had before. Um, and I'll go ahead and go up here and copy this. So now it's not a function, it's a particular value. We just don't know what the value is. Um, and what that enables me to do is to say, okay, well, if it's some specific value, then I can say the change in U star, if U star is a constant, it has to be equal to 0, right?
Mm-hmm.
So if I've said already that U star is a fixed number, and then I say, okay, let's talk about changing U star, then I say, what would the change in U star be? Well, it has to be fixed at 0 because a constant can't change, right?
Yeah.
Right? Like if I tell you, I don't know, um, so how tall are you, Miriam? Do you know?
5.
You're 5 feet.
Yeah.
Okay. Okay. Well, that's a constant, right?
Yeah.
So if I say, I mean, at least within reason, let's not get outrageous here and talk about maybe you stretch overnight or, you're going to shrink as you get older or whatever. But, for all intents and purposes, for the next couple of days, your height is fixed at 5 feet. And so if I say, how much is your height going to change? If it's fixed, it's going to change by 0, right? You're not going to grow an inch. You're not going to shrink an inch. You're stuck at 5 feet. Your change is 0, right?
Yeah.
Right. But that's the left hand side of this equation. Okay. The right hand side, we could change, right? As long as we change it so the value's always stuck at, we said like some fixed number like 10. And so now what we're talking about is exactly what we said before. All along a given indifference curve, the utility is constant. I can change how much, remember the axis down here is X, right? The commodity X, and the vertical axis commodity Y. I can change how much X and Y I consume, but if I'm going to stay on one indifference curve, I have to hold U constant. So changing X and Y is allowed, but changing U is not on an indifference curve. So this equation with the change in U being fixed to 0, now I'm on a particular indifference curve, okay? But the nice thing about that observation, so I've just mathematically described an indifference curve by saying, any change, and the D here stands for change. It's, delta change. Change in U's got to be 0, okay? So now what I can do is say, oh, okay, well then how can I change the stuff on the other side of this equation? So if I just in general say, okay, d u star is equal to, well, and now I guess I'll go ahead and write this generally. On the right-hand side, we have that it's some function of x and y, some unspecified function, right? This is the Cobb-Douglas form up here, but now I'm just talking more generally, like for any possible utility function. You see here, this is the Cobb-Douglas version, right? And this is just speaking more generally, right? Do you see what I mean?
Yes.
Okay. So I'm gonna go ahead and be a little bit more careful here because I kind of got a little bit ahead of myself. So, for some general utility function. And then we'll bring it back to the Cobb-Douglas one. So now I'm going to go ahead and take this. Okay, and I'll copy this and start a new screen. So more generally for any U, we can define a particular, and I'm going to use IC for indifference curve by letting du equal 0. Okay, so okay. So I'm going to say, again, I'll use du star. And now this is kind of the next thing. And if you guys have had calculus, this will make a lot of sense to you. If you haven't had calculus, then maybe not. So, but intuitively, it should make sense when I say the following. So if we're going to change the right-hand side, okay, and for those of you that have had calculus, what I'm doing is I'm taking the total differential of x. But if you're not familiar with that, or maybe haven't taken multivariate calculus, you haven't heard of total differential yet, but that's fine. What I'm going to say is I can change f, so that's df, by changing x, right? So that's a change in f by changing x. And for those of you that are familiar, that's going to be the partial derivative of f with respect to x, by multiplying that by the change in x. So that's just one way of changing it. The other way I can change it is I can change f by changing y and multiplying that by the change in y. So this is the part that's going to be a little bit subtle. So see if you follow me, Miriam. So I say that we could change u, but we're going to make sure this is fixed at the change of u is equal to 0. We just haven't substituted in 0 yet. Okay?
Okay.
And then I'm saying over here on the right-hand side, we have some general function, and that function can change, but it's either going to change because we change the amount of x or we change the amount of y. That's the only thing we can do, right?
Yes.
I mean, these are the two variables for the function. And so if the function is going to change, it's either going to change because we change x or we change y.
Mm-hmm.
So that's all this says on the right-hand side is it says, okay, I can change f, which is df. And this is df divided by dx, but notice that I then multiplied it by dx, right? So those two would cancel, right? And you would just end up with df. And so it's just a nice way of writing. I can change f a little bit by changing x. Over here, it's saying, you know, I can change f by changing y. But again, remember, here you've got df divided by dy times dy. So these would cancel, right?
Yes.
Yeah. So it says mathematically exactly what I said in words up here, which is I can change this function by changing x a little bit or by changing y. That's it. You know, it's just a simple, you know, mathematical equation that describes in words what's very intuitive. If you're going to change a function of x and y, you've either got to do it by changing x or by changing y. That's it. but we're more explicit here with the math. The other thing that you should know, or that you're going to have to know. So this is kind of like the calculus explanation, but in terms of the economics, what we would do next is make the following observation. Okay. So one is that we have a special name. When we change utility, remember this is utility function, by changing one of the consumption goods, we have a special name for that. We call that the marginal utility of X. And we have a special name for changing utility as you change the amount of some other good Y, and we call that the marginal utility of Y. Does that make sense, Miriam?
Yeah.
So now we're gonna go ahead and say, okay, again, we have du star, we make our substitutions, and we'll say it's gonna be mux times dx plus muy times dy. So you see the simple little substitution that I made there?
Yeah.
And then we're going to say, well, we know by definition, since we're on an indifference curve, the du, the change in utility, has to be equal to 0. And so we'll substitute that in. Well, let me do a little bit better with my notation. Times dx plus muy times dy. Okay. And now things are starting to look interesting, because I'll make the following observation, and that is that, do you remember the definition of slope?
Not quite, but I know the formula.
Well, tell me.
Is y equals mx plus b.
Well, okay, that's the, so y is equal to mx plus b is the slope intercept form of a linear equation, where the m is the slope. But do you ever remember anybody ever telling you, I know you're going to know this as soon as I say it, right? The slope is equal to rise
Overrun.
over run, right?
Yeah.
Right. Well, the rise variable is what variable? Do you remember? Rise is, we're measuring it on the vertical axis, right?
X.
So that's dy, the change in y, right? So okay, I'll help you out here a little bit. So remember, this is the y-axis, and this is the x-axis, right?
Mm-hmm.
And so if I talk about rise,
Okay. Yeah. I remember.
I'm going up and down, right? And if I talk about run, I'm left and right, right?
Yeah.
So this is rise is measured by how much things change. So dy is just the change in y. Okay. And run is measured by the change in x. Okay. So, you probably have to go back, maybe do a little bit of like algebra review thing or whatever, if this is still a little bit mysterious. But, for the slope of a linear equation, so if we talk about the blue line here,
Mm-hmm.
I'll do this in light blue, right? If I'm going to measure the slope of this, I have one point and then I go down some distance, and I'm changing in the y dimension, and then I would go over some amount in x, right? And I would just be measuring the slope of the line using these, and I'll try to pick a special color, going from this point to this point on the blue line. You know what I mean?
Mm-hmm.
Does that make sense?
Yeah.
Yeah, so we're just saying I start out here and I can measure those, it's, that point's associated with the amount of x and the amount of y. And then I go to this point and it's associated with this amount of x and this amount of y. And I can take the difference between those two and I can calculate my rise and my run. And that's what dy over dx does, is it calculates that change. So I know all of you know this because I know all of you went through the same algebra and geometry classes that I did. And if for some reason it doesn't make sense, it's supposed to be super simple. So, if you haven't done it at this point, you should spend, 30 minutes on Khan Academy, or go back and review something from, your early algebra class, because it's not supposed to be complicated. Okay. Are you good, Miriam?
Yes.
Okay. So yeah, we know that rise over run is generally how we measure slope, which is going to be dy over dx. And since we did everything properly here with our dx's and dy, all we have to do is solve this equation here. And I'll use a little stamp. Solve that equation for dy over dx. So let's go ahead and do it. Dy over dx is equal, right? So if you think about it, it's pretty straightforward. I would take everything here on this right-hand side, right? And I would subtract it from both sides. Actually, I'll go ahead and go through the steps just so everybody can follow. So let me go ahead and back up a little bit. And okay, so and so that's what I want to solve for, but I'll go ahead and do the steps. So the next step would be minus MUY times dy is equal to MUX times dx. Does that make sense, Miriam? I just subtracted that from both sides, right? So 0 minus that just leaves that, right? And so then I'm going to go ahead and divide both sides by minus MUY, right? And then I'm going to divide both sides by dx, and then I'll end up with minus MUX divided by MUY. Okay. So this equation describes the slope of the indifference curve generally. Okay. So the slope of the indifference curve is always going to be the marginal utility of x over the marginal utility of y. Now, the one other thing that I want to point out, so for Cobb-Douglas, remember that u is equal to x raised to the alpha times y raised to the beta, a or b, right? And the marginal utility of x is, by definition, we said it's going to be du dx, right? And this is something that if you don't know any calculus, you'll have to memorize this formula. If you do know calculus, then you probably remember the power rule, and this won't be a big deal. For those of you that don't remember the power rule from calculus, have you had calculus yet, Miriam?
No.
Okay. You're gonna take the business calculus then probably pretty soon, right? Yeah. So they're gonna teach you this thing called the power rule, and I'll show you here. Power rule. And all the power rule says is that if you have a function f of x, and generally f of x is going to be something like, let me try to think of some good, I'll say some coefficient. No, I'm not going to use d. I would normally use Greek letters here, because we're running out of symbols. But let's say it's n times x raised to the m power. Okay, does that make sense, Miriam?
Yeah.
That's the function. And so for a function like that, generally, if you calculate the change, which is df dx, the change in f as you change x, then the way you do that, the formula that applies is you take whatever the coefficient was n, you just leave it alone, and you multiply m minus 1, oh, excuse me, times m. Let me get my parentheses here, right? M to the x raised to the m minus 1 power. Okay. Okay, so that's just the formula. And they'll explain to you in calculus why this formula makes sense. But whenever you have subfunctions, so I'll give you an example. For example, let's say f of x is equal to x squared. That's sort of like the simplest example, right? Well, in this case, right, the coefficient in front of x is just 1. So I could write this as if I want to be more explicit, is equal to 1 times x squared. Does that make sense, Miriam?
Yeah.
Right? So now if I want to calculate df dx, then I just apply the formula. And remember, the n is left alone, so I'll still have 1, but I'll multiply it by the exponent, which is 2, and then I'll have x to the 2 minus 1 power. And then I just go ahead and simplify things. And 1 times 2 is 2 times x to the 2 minus 1 is x raised to the 1 power, right? And any number to the raised to the 1 power, you don't really need the exponent because that's implicit in the way that we write things. So this is 2x. Did that make sense, Miriam?
So it's just basically you just multiply whatever the constant. I mean so on the second part, just subtract your constant from your
Yeah,
from the
so this is the exponent, right? And
minus.
this is the coefficient, right?
Okay.
Right. So you just take the exponent, you
Minus the
multiply it by the coefficient, and
okay.
then you take the exponent and drop it by 1
Oh,
power, right? So here we had for x squared, there's implicitly a 1 in front of there, right?
mhm.
So it's just 1 times 2, which is 2. And then if you take x squared and then take off 1 unit from the exponent, the 2 becomes a 1, and you just end up with 2 times x.
Oh, okay. So like, because in the second part where you have the 2 minus 1, is it always going to be minus 1 or does it depend what your coefficient is?
Well, see,
Oh, yeah, minus 1.
it's always minus 1.
Oh, okay.
Yeah. So if it was, we could do one more example. Um, but so let's see. Let's do another example, and we'll say some function g of x is equal to 2 times x raised to the 3 power, right? And then we want to calculate dg dx, right? So then I'll do 3 times 2, right?
Mm-hmm.
Which is 6 times x 3 minus 1 squared.
Oh, okay.
You see?
Yeah.
Ta-da. So, and you'll learn this in calculus, but the only reason why we bring it up is, remember, our definition of the marginal utility of x actually is the derivative of the utility function with respect to x. Things are a little bit different here, though, because remember, our exponents are fractional. And so we're going to have like 0.2 minus 1, and we'll get minus 0.8. So we'll have negative fractional exponents. So a lot of times people get a little bit freaked out because they don't remember their exponent rules and things like that from algebra. And so dealing with negative exponents and stuff like that isn't something that they're, it isn't handy for them. But if you're one of those folks sitting in the class, I say, go back and review your exponent rules and negative exponents and get ready, because you're going to see them a lot in this section of the class. So you don't have to know the calculus, but you got to memorize the formulas, and you have to know how to work with negative exponents and fractional exponents, which is a prerequisite for being where you are right now. So go back and review it if it's not handy. Okay, so du dx in this case, the only thing that's a little bit different is that now we have a coefficient that doesn't include x, it includes y. And we know that y is a variable, but with respect to x, it's constant. So y isn't changing with x, they're independent of one another. So we treat this, when we're looking for the change in u as we change x, we treat the y raised to the beta power like it's a constant, like it's a coefficient. So here, we're going to go ahead and use the same power rule formula, but So we'll have our constant out in front, or coefficient in front, and then we multiply it by the exponent on the variable, which is a in this case, right? And then we go ahead and take x raised to, and maybe it'll be a little bit easier if I use some square parentheses here, so things aren't confused in terms of what parentheses go with what. It's a to the minus 1, and there you go. So does that make sense, Miriam?
Yeah.
Okay. And likewise, for the marginal utility of y, remember it's going to be du over dy. And I'll tell you what, I'll let you all calculate this one and we'll talk about it in just a minute. So Miriam and Derek, you with me, Derek? I know you're there.
Yep.
Okay, so go ahead and tell me what the formula is for the marginal utility of y. I'll give you like 2 minutes, okay, to think about it. Just tell me when you're ready. You can
Can you
type.
just move a pink arrow?
What's that?
The pink arrow?
Oh, you want me to move it? Okay, sure. Okay.
The x to the a times b parentheses y to the b minus 1.
Okay, hold on. Wait a minute. I'm going to type what you said.
I can try to do it in the chat.
Okay, so I should type a parentheses and then what should I put?
X to the a
X to the a
times b parentheses or bracket, yeah, y to the b minus 1.
What do you think, Miriam? Do you agree with Derek? Does that look good to you?
Yeah.
Yeah, that's right. Now, the thing that I want to point out is, remember, for the indifference curve, what we're trying to do is calculate the slope of the indifference curve for our tangency condition. And remember, it's going to be minus MUX over MUY, right? And so we have to take the ratio of these two. And the next thing that we should calculate, and I'm going to go ahead and go on our next board here. So and okay. So the thing that I want to point out to everybody here is that there are a couple of things that will be useful now that we know that this is Cobb-Douglas, right? Right. So since it's Cobb-Douglas, that implies that A plus B is equal to 1. Or, right, that A minus 1 is equal to minus B, right? And and b minus 1 is equal to minus a. So do you see how that is helpful? Because what it means is when we have mux over muy, and so that's going to be and I'll put this all in curly braces. Okay. Then we can go ahead and do some substitutions to simplify all this. So the first one would be that a minus 1 is actually minus b, right? Are you following me, Derek?
Yeah.
And then b minus 1 is minus a, right? So then hopefully you remember from your negative exponent knowledge from algebra that, and I'll put it up here, that some number x raised to the minus 1 power, for example, is equal to 1 over x, right? And if I was to say x to the minus 2, then it would be 1 over x squared. Do you remember that, Derek?
Yep.
And what about you, Miriam? You
Yeah.
on board? Yeah. So now we can go ahead and rearrange things. And so see if this makes sense. So I could put 1 over x raised to the b power there. That's fine. And again, if I want to be careful with my parentheses, and I could put y 1 over y to the a power there. Are you all good, Derek? Does that make sense, what I did?
Yeah, just to get rid of the negative exponent.
Yeah. And then I can simplify even further, right? Because I have, notice, right? I have y raised to the b times a times 1 over x to the b. So this is really just y over x raised to the b power. And likewise over here, it's x raised to the a times 1 over y to the a. That's just x over y to the a, right? And so I'll do one more. One more line of this before we get to our final result. So I'm going to say this is y divided by x. And I'm going to change the parentheses around here a little bit. So check my algebra and see if I goofed up anywhere, which I'm pretty sure I didn't. I'm just rearranging things. Okay. And x divided by y. Okay. All right. Well, so this is starting to look pretty interesting, right? We have A over B, right? And then let's see if I can be a little bit more explicit about this. Maybe this is better. Okay. How do you like that, Derek?
That's fine.
Okay. And so the last thing that we want to point out, right, is because A and B are going to be equal to 1. If you look here, I have y raised to the A power, right? And so, and here I have y raised to the B power, but here it's raised to the A power in the denominator, and here it's raised to the B power in the numerator. So, well, I'll let you guys work out the bit of algebra that we said. But what this reduces to, and it's a little bit hard to do it here on this screen. Is MUX over MUY is equal to alpha y over beta x. Okay, so you all, probably have your notes there, and you can scratch this out. I'll show you. I don't know if there's anybody that doubts the result, or if you all are fine. So, is everybody okay? Does anybody have any questions?
Can you move it down a little? I can't see that.
Oh, hold on, wait a minute. Maybe this will help. Can you see that now?
Yeah.
Okay. I don't know. Hmm. Okay. So these are the last few lines of algebra, which are hard to do on this whiteboard. But if you all can follow, I wrote what's on the screen there. And then if you go there, there's b in the denominator. So what I did here in the numerator, right, is this is a fraction. So if you invert and multiply, then you invert the fraction and can take it up into the numerator. Okay. And then you have, in the numerator, you have x to the alpha and x to the beta and y to the alpha and y to the beta. And then you multiply those by each other. And then alpha plus beta is equal to 1. So you get y to the alpha plus beta over x to the alpha plus beta. And that just becomes y over x.
You're intending to share something else other than what you typed?
Oh, well, yeah. Can you see my video?
No.
Oh, you can't see me?
I can see it.
Hi. You can't see me, Derek? Can you see me wave my hand? Are you there, Derek?
I got it. I got it.
Yeah. So anyway, it's a little bit hard to do it here on the screen, but the last part of this is just recognizing that this is in the denominator, and it's a fraction in the denominator. So we can invert and multiply, and then you end up with, well, I'll do the line here and see if you all are okay with it. I'll do the missing step. Okay. Okay. Okay, so we got this first part here. Well, I'll just modify this whole thing. Okay, so here, hopefully everybody can see clearly that this is a fraction divided by a fraction. So we can invert and multiply here, and maybe actually, well, there's no good way to do the notation on this, but maybe this is a little bit better. You all tell me what you think. I'm going to write y raised to the beta and x raised to the beta, and then I'm going to get rid of that, and then raised to the a, raised to the a, get rid of that. Okay. And now we have a fraction divided by a fraction, right? So let's just do the a over b here, pull that out, and then we can get rid of that. And now, okay, so now we just have this fraction. Are you following me, Derek? Divided by this fraction. I don't know if anything got crazy, but notice that I can change that division symbol, right? And I'll just do one more line because why not? We've already gone this far, right? Might as well bring it home. Okay. So we are here. And so I can change this to a multiplication symbol by inverting. And then notice, right? I've got, and I hopefully you can see this. Can you confirm, Derek? You can see it's this fraction multiplied by that fraction. So I just multiply the numerator times the numerator and the denominator times the denominator. Does that make sense?
Yep.
Yeah, and so and so then if I have y raised to the beta times y raised to the alpha, then that's y to the beta plus alpha, and x to the beta times x to the alpha is x to the beta plus alpha. And then I can get rid of this. And I don't need these anymore. And then remember, beta plus alpha is equal to 1. So lo and behold, we have A divided by B times Y divided by X, and voila, right? We get our final result. So what do you think about that, Hannah?
Beautiful.
Beautiful. What about you, Miriam? Are you
Yeah, I'm still here.
amped?
I have a question though.
Ah, okay, Hannah.
So are all these steps you were just showing us how to get the MUX over MUY, or
Yeah.
we're going to have to do all these steps because,
Oh,
or
okay.
was this just like a longer rendition?
No, okay. So there's 2 points here. Okay, I'll tell you first what you and I have to know, and then I'll tell you like why I did this. Okay. So obviously you guys have this on video. You could follow all the steps of the algebra, and you can do your own cases and verify that what I'm saying is true. Okay. But what do you have to know? Well, you have to know that MUX over MUY is the slope of the indifference curve. That's point number 1. And in the case of the Cobb-Douglas, remember, this is the Cobb-Douglas, algebra only for the Cobb-Douglas. In general, it's MUX over MUY. That's the marginal rate of substitution or the slope of the indifference curve. That's point 1 to know. Point 2 is this is the way it looks for Cobb-Douglas. I thought about doing this before. There are a couple of other really common utility functions other than Cobb-Douglas. One of them is called the CES, or constant elasticity of substitution utility function, but it's like more complex than Cobb-Douglas. And there's another one called the exponential utility function, which again is like probably more complex. So I thought about adding in other utility functions into the class, just because I didn't want people to think that Cobb-Douglas was the only utility function that existed. But as you can see, it takes time. So I've limited it to Cobb-Douglas, but you should know, because you might come into another class where they want you to calculate a consumer optimization problem for like a different type of utility function, and it's not going to be Cobb-Douglas. So the technique, which is, let's see here, tangency, right, and budget. But in general, the tangency condition doesn't look like this. What the tangency condition looks like is, and maybe I should have written it first generally, but the tangency condition we put generally last time is the MRS is equal to PX over PY. And the MRS by definition, and I told you guys this last time, I'll just write it one more time really quickly over here. MRS is equal to MUX over MUY. The MRS is the slope of the indifference curve, but again, kind of like one of the things that's a little bit of a pain, and you have to pay attention to this on some of the problems, because in Inithium, they're explicit, is that remember, the slope of the indifference curve is actually minus MUX over MUI, and the marginal rate of substitution is the absolute value of that. I talked about this last time, but anyway, so the big picture is, what you have to know is that in general, right, the tangency condition is this, and that's how we calculate it, the ratio of the marginal utilities. And so, and then in the case of the Cobb-Douglas, you should know that it takes this specific form, right? Because you're going to need that to solve the problems. But the one other thing that's kind of a little bit hidden, and actually I've asked this question on an exam, because it's not one that's on Ignithium, but I've asked folks to actually calculate the marginal utility of tacos, for example, or the marginal utility of tequila. Now notice that, and we don't have quite enough time to do it today because we're over time already, so I suppose maybe we'll do it next time. But when you do that, you're calculating the marginal utility at a particular point on the utility function. So you have to substitute in the amount of X and the amount of Y. So what do you need to know? Marginal rate of substitution, slope of the indifference curve, what it looks like in the case of Cobb-Douglas, how to calculate marginal utility. That's what you need to know. Now, you know, why did I go through all this? To show you, and just saying, oh, you need to know these 4 formulas, you know, just memorize those. Well, because actually, you know, I don't want you to, I want you to know how to solve a consumer optimization problem, but also I want you to know that this isn't something to take on faith. You know, oh, Dr. Hunter said it's alpha Y over beta X. Hannah, do you ever remember, you know, logical fallacies? I don't know if you studied them in philosophy or any of your other courses.
Is that like an ad hominem?
Well, ad hominem, yeah, actually that stands for like attacking the person, right? Rather than the idea or discussing the idea. But yeah, so some at times ad hominem attacks get counted as being part of, you know, fallacious reasoning. But one of the other ones that's really common is appeal to authority, right? we're not supposed to do that in college. It's supposed to be critical thinking. So I'm supposed to describe to you why it is these things, that I believe are the way they are, right? Not just, just memorize this formula and go on about your business. Because if I do that, then when Hannah is my age and she's running some huge biotech firm or whatever and trying to figure out something that nobody else has ever figured out before, she's not going to be able to find that as a formula in a book. She's going to have to think, oh, well, how did people solve problems in the past? What techniques did they use, So that's what higher education is all about, is critical thinking. So if I don't explain to you, how we're doing these things, where the formulas come from, then you'll never be in a position to really, expand on that knowledge. So, so the answer is, why am I doing this? I'm doing my job. I'm doing it the right way. So, anyway, okay. Well, that's enough for today. I hope you guys have enjoyed this as much as I have. And I'll see y'all next time. Anybody have any questions, final questions? No? Okay.
Nope, I'm good.
Okay. All right, everybody. Take care.